Okay, after some severe issues with the mic and everything, I'm finally in a state where I can record this bloody video. So here we go. I made these slides for something else, but that did not materialize, so I thought I might as well still make use of these slides. So naturally I thought I'd make it a video. Um, and yeah, of course, the title is Generalizing 21 Dares. Um, And yeah, this is a problem that I worked on maybe a couple of years ago, but I'm only making a video on it now. But okay. Either way, it's somewhat interesting. You might find it interesting. Okay, so the game 21 Dares itself is a game where you have two people. They can add any number between 1 and 3, and the first person to say 21 loses. So basically, what that means is the person who says 20 is going to win because that forces the next person to say 21, which means that they have to do a dare, or traditionally in the game it means they have to do a dare. So okay, what we're getting from this is that we have to say the number 20. In order to say the number 20, we also have to say the number 16, because if we say 16, then our opponent says a number between 17 and 19, and then we can, no matter what, we can guarantee that we say 16. Sorry, 20. And so, okay, so we need to say 20. In order to say 20, we need to say 16. So in order to say 16, we need to say 12. To say 12, we need to say 8. To say 8, we need to say 4. And to say 4, we need to go second. So, what do we gain from this? This means that we can guarantee a win in 21 dares if we go second and we just go up multiples of 4. So, that's cool, but what happens if we play... First of all, what happens if we play X dares and we can add any number up to Y? Which is not too difficult, but what the difficult question is, what if there's n people? What happens then? And here we grapple with these questions. So first we'll do it with 2 players, and then we'll move on to more than 2 players. Okay, so in a game of X dares, I need to say X minus 1, and that forces my opponent to say X. Now since my opponent can add Y, then I also have to say X minus 1 minus Y plus 1, because then even if he adds Y, then I just add 1 and I get to X minus 1. And if he adds 1, I just add Y and I get to X minus 1. And any number in that range, I'll be able to get to X minus 1. And so using similar reasoning, I have to say X minus 1 minus 2 times Y plus 1. And I have to say X minus 1 minus 3 times Y plus 1. So on, so on, so on. So what do we notice? We notice that X is congruent to X minus Y plus 1, it's congruent to X minus 2 times Y plus 1, it's congruent to X minus blah blah blah, mod Y plus 1. So, because we're working kind of more general than just 21 dares, I thought it'd be easier to just use this notation that I've come up with. Not very original, but okay, it does the job. This kind of equivalence class of X with respect to Y, meaning the set of all integers between 0 and x, such that n is equivalent to x mod y plus 1. So, for example, and the reason that this set is so important is because in 21 dares, for example, we set x equal to 20 and y equal to 3, and the set becomes the set of all integers between 0 and 20, such that n is equivalent to 20 mod 4. And since 20 is equal to 0 mod 4, this is just the set of all multiples of 4. So, here are some observations. Firstly, this set gives us all of the numbers that we need to say in order to win. 4, 8, 12, 16, 20. Secondly, 4 is the key number here. Not, well, obviously 20, all of them are key, but 4 is the real key. Because the first number dictates whether we want to go first or second. Now in this case, because 4 is greater than 3, we want to go second so that we can guarantee that we say 4. But this isn't always the case. So we have to look at the minimum of our set, sort of like the equivalence class of x with respect to y, we have to look at the minimum of that, and then that will determine whether or not we go first or second. So, in a game of first to X, so 21 dares is first to 20. Between two people who can go forward by at most Y, then player 1 wins, so we want to go first. If the minimum of this set, of these congruency classes type thing, if the minimum of this set is not equal to Y plus 1, then we want to go first. So in 21 dares, the minimum of this set, so 20 with respect to 3, is 4, which is 3 plus 1. So we don't want to go first. But if the minimum of this set happens not to be equal to Y plus 1, then we do want to go first. And an equivalent statement of this is, if we're playing X dares, then to check if we want to go first, all we see is X minus 1 a multiple of the amount that we can add plus 1. So in 21 dares, is 21 minus 1, 20, a multiple of 3 plus 1, 4. Is 20 a multiple of 4? Yes. Okay, we want to go second. But otherwise, we want to go first. So for example, if I'm playing 101 dares, and I can move by 8 each time, then I see, okay, 101 dares, so I want to check, and I can move by 8, so I want to check, is 100 a multiple of 9? No. Okay, so I want to go first. And then to see what I want to say, now that I've established that I go first, well, I work out the minimum of this set. And the minimum is just 100 mod 9. And 100 mod 9 is just 1. So I say 1, then I say 10, 19, 28, so on and so on. And eventually I'll say 100 and I'll secure the victory. And so it's much easier to do this than to just subtract 9 until we finally hit 1. 91, then we go down to 82, and then we go down to 73, etc., etc. It's much easier to just work out, okay, I need to do 100 mod 9. Okay, that's 1, done. So, okay. So the general work is somewhat helpful if we're dealing with larger numbers. And, okay, that kind of wraps up 2 players. If x minus 1 in X dares is a multiple of Y plus 1, then we want to go second, but otherwise we want to go first. Okay, cool. It gets much trickier though, unfortunately, when there's 3 plus players. Because now, okay, when there's 3 players, first things first, to win I don't have to say 20, to win I can say 19, because between the 2 of the other players, they'll get to 21. The question is, how do I get there? Because if I want to say 19 or 20, well, the other 2 people can make sure that doesn't happen, basically. And so the question becomes not when do I win, or when can I guarantee a win? But it becomes, is it even possible for me to guarantee a win? For example, in 21 dares, the standard game with 3 people, if I say a number between 14 and 18, well then I'm screwed, because then they just force me to 20 if they want to. And if I say a number between 8 and 13, well then they just force me to say a number between 14 and 18. And so on and so forth. So between the 2 of them, if those 2 want to beat me, they will, basically. And so in normal 21 dares with 3 players, I'm screwed, unless I form a partnership with my friend. So, when can I win then? Like, is it even possible for me to guarantee a win in any of these situations? Well, here's our first big restriction. If we have a game of X dares with more than 2 players, okay, where everyone gets a go. So I'm not playing 21 dares, but everyone can add 20. Everyone gets a go, and there's more than 2 players, then immediately it's impossible to guarantee a win when Y is greater than 2. Immediately. So, let's prove this. Since there's n players, we want to say a number between x minus n minus 1 and x minus 1. Why is that? Because if we say x minus n minus 1, well then there's n minus 1 players, so even if they all add 1, they still get to x. One of them loses. And if I say x minus 1, obviously they're going to lose. So I want to say a number in this range. And so we need the player before us to say a number between x minus y minus n minus 1 and x minus 2. Because if he says this number here, I just add y. And if he says x minus 2, I just add 1. So we want the player before us to say a number in that range. Here's the next detail. It's only possible to force this when I say x minus y minus 2 times n minus 1. Because otherwise, everyone will just add 1 and they'll stay outside of this range. So, I say x minus y minus 2 times n minus 1. And now, the only way for them to stay outside of this range is if the maximum they can add exceeds x minus 2. That is when the following inequality is true. X minus y minus 2n plus 1, 2n minus 1 plus y times n minus 1 is greater than or equal to x minus 1. Now we can do algebra. So, firstly we can combine these y terms to get y times n minus 2. We expand everybody, we can cancel out the x's and subtract 2, add 2n, and okay, somewhat simple algebra. We get y is greater than or equal to 2n minus 3 over n minus 2. So, what does this mean? The amount that we can add, it's impossible to guarantee a win when the amount that we can add is greater than or equal to 2n minus 3 over n minus 2, where n is the number of players. Now, when n equals 2, obviously y is never going to be greater than this fraction when n equals 2 because it just blows up. So that's the interpretation for why it's always possible to win when n equals 2, when there's 2 people. When there's 3 people, we can win when y is less than 3. Now, the rest we can do with calculus. So if you take the derivative, you'll see that it's minus 1 over n minus 2 all squared. Minus 1 over n minus 2 squared. So the function is strictly decreasing when n is greater than 2. And also the limit as n goes to infinity is precisely 2. So that means that this fraction is always within the range of 2 and 3. But the important part, I think, is this is both of them are important. But importantly, it's always greater than 2. So it's impossible when y is greater than this fraction, but this fraction never quite reaches 2. So this fraction could be, for example, 2.5. So it's impossible when y is greater than or equal to 2.5, but 2 is obviously not greater than 2.5, so it's still possible when y is equal to 2. And so what this means is y can be 2 or 1 for all n greater than 2. So, okay. That's a pretty big restriction though. What we're saying here, essentially, is when there's more than 2 players, we have to add either 2 or 1. We can't add 3, otherwise they'll screw us over. Okay. But it's not over, because for any game of X stairs with n players, we still can't guarantee a win if anyone can add at most 2 every turn. Because the next problem is how do we guarantee that we can say this number here, x minus y minus 2 times n minus 1? Because remember, we have to say this in order to get into the range that we want. And it turns out this is only possible if it's either available on your first go or y is equal to 1. So let's let's see why this is true. Well, we require the person before us to say a number r in the range of either x minus 2y minus 2 times n minus 1, because then we can just add y and get our required number, and x minus y minus 2 times n minus 1 minus 1, because then we just add 1. Okay, therefore, we must say x minus 2y minus 3 times n minus 1, because then if we don't say that, then everyone just adds 1 and they stay outside of the range that we want. The only times this works is when they stay in the range even after adding the maximum that they can add. And this holds when the following is true. This thing plus y times n minus 1 is greater than or equal to x minus y minus 2 times n minus 1 minus 1. Sorry, less than that, which is the top end of this range. After we do some algebra, cancel out the x's, do all of this funny business, we end up with n minus 2 greater than y times n minus 2, and we cancel out the n minus 2's because n is not equal to 2, and we end up with y is greater than or equal to 1. Sorry, 1 is greater than or equal to y. So, let's conclude. We have a game of X dares with n players where we can add up to y. Then, we can guarantee a win if there are 2 players, or there are any amount of players, but everyone can add only 1 each turn. Kind of a dead game. Although, I guess, it could be good. I'll let you decide that. Or, you can say x minus y minus 2 times n minus 1 on your first go, and y is less than or equal to 2. And I'll leave it as a small exercise to the reader to do the algebra to find n in terms of x. Set y equal to 2 and find n in terms of x. So you can figure out exactly how many players are needed for this as well. Using this inequality here. And y is less than or equal to 2. So, my personal recommendation is, I know because you're watching this channel that you are an extremely cool fella, and you have loads of friends, but I would recommend that you keep it to just one friend, because it's going to be hard to convince everyone to add at most 2. And also you're going to need a lot of friends to perform that. For example, even in plain old 21 dares, I need 10 players that can all add up to 2, because then on my first go I say 1 and I won't lose. But I need 10 players, and that's if it's 21 dares. For example, if we're playing 100 dares and everyone can add up to 2, you need, I believe, 49 players. So, there you go. Yeah. But yeah, okay, that's it. Thank you for watching. But hold on, don't go, because I have an interesting food for thought, actually. What if we play 21 dares but in a group? Now, the first question that springs to mind is, what conditions have to be imposed on this group for the game to make sense because, for example, it has to be ordered because otherwise there's no notion of adding any number up to 3 if there's no order. For example, we can't play it in the complex plane, unfortunately. But also, we can't play it, for example, in the rationals because if I'm saying first to a half, you can add any number up to a third. I say a third, and then you say like a billionth, and I say a trillionth, and you say a quintillionth or whatever. And we're never going to end by the nature of how those sums work. We're never going to get to a half. Um, so we also need some sort of condition on the sums, such that kind of any infinite sum diverges. Like for example, in the integers, you can't have an infinite sum of integers that converges unless unless we're including negatives. But okay, apart from that. Naturals then, natural numbers. Doesn't have to be a group, it can be a monoid, I guess. Monoid is probably better, actually. But yeah, that's food for thought, I guess. How would you play this in a group? Or a monoid, sorry, it's probably better to play in a monoid. But anyway, yeah, thank you for watching. I promise new materials on the way. Um, yeah, apologies for the lack of new material, but it's on the way. Okay, see you shortly.